Good morning, Pre-Calc students. I hope that you guys had a great St. Patrick's Day yesterday. This recording is going to go over 3.3, Harmonic Motion, and this is the last section before your Unit 3 test. So I put a little activity up there on the board. If you'd like to pause this recording and try my little activity, it's kind of fun. It says, here's a creepy activity. Can you find the man in the coffee beans? And I have to tell you, I had to look for quite a while before I was able to find his face. So if you'd like to participate, go ahead and push pause, try and find him, and when you're ready for the answer, go ahead and press resume. For those of you that are trying this, the hidden man is right here. So there's his nose, his eyes, his face. There he is. Okay, so anyway, I guess today's 3/18 since it's Tuesday. So let's go ahead and get going. This is week 10. So our essential question for this week is asking, what is the difference between frequency and period of a sinusoidal function? So by the end of this session, you'll be able to know the difference between frequency and period, and that is what the answer that you'll put in the drop box for week 10. So some topics that you're going to see showing up on your 3.3 quiz are those listed on the screen. So let's quickly go through them. It says to know examples of simple harmonic motion. So some of those include springs and pendulums. We're going to be doing examples of each today. Next, you want to be sure you are able to identify the form of an equation that models simple harmonic motion. And those would be when we have a cosine or when we have a sine. We'll go over what each of these letters mean in just a minute. You need to be able to identify frequency, period, initial position if I give you the equation. And lastly, you'll be asked to find the model, meaning can you write the equation if I give you the initial position and the amplitude and the period. It's basically plugging in these numbers. It's just saying, can you plug in A, can you plug in omega, and write your equation that models that function. So over here, here's Mr. Smurf. He's saying, do you speak Greek? When we see this sort of cursive looking W, that actually means omega, and we're going to learn what omega stands for in just a couple minutes here. So here are your two basic harmonic functions. Let's go ahead and write them down. And sorry, these are true W's on here, but they should be omega signs. So our cursive W's here. So we have A, which I'm telling you is the amplitude. What amplitude is, it's your maximum displacement from equilibrium. So think about something that's in motion. Before it moves, it's in a state of balance. It's at its equilibrium point. After you push or pull on it, it's going to be displaced from that original setting. So that's what we're talking about. Amplitude is going to be the maximum it gets displaced from its original starting point, from its equilibrium point. Our period is going to be 2 pi divided by omega. So basically, we're going to be using this formula quite a bit today to solve for omega. Because think about back from mathematics, right? How would I get W by itself if it's in the bottom right now? If here I have period, and I have 2 pi over W, or 2 pi over omega, I should say. If we're trying to get omega by itself, I first need to get it out of the denominator. So I'm going to multiply both sides by omega. And then, sorry, I'm going to move down here where I have more space. So if I have omega times the period equals 2 pi, to get omega by itself, I'm going to divide both sides by the period. So now I would get omega equals 2 pi divided by the period. So we just manipulated an equation that we knew to be true, an equation that they gave us, to get a different variable by itself. And the reason we wanted to be able to do that is because if I ask you to plug in A is really easy to find on your graph. Again, it's just the maximum displacement, so we'll talk about that in a minute. But then you have to fill in your omega. Well, how are you going to find omega? Here's how. You're going to plug in 2 pi divided by the period. And we learned last unit and the beginning of this unit that a period is one whole cycle, or one entire oscillation is what they're going to call it this unit. And then lastly, frequency is going to be 1 divided by the period, or in other words, omega divided by 2 pi. In this case, when we're talking about pendulums and pendulums and springs, they're going to use the word oscillation. And that's a really good word. We're going to show you why in a minute. But oscillation just means it's going to go back and forth, back and forth, back and forth. It's going to oscillate. So let's pretend I have a spring right here. You could pull on the spring and let it go, and it's going to bounce. Or you could push the spring up, and when you let it go, it's also going to bounce. The equilibrium never changes. It's always going to be at this center point when it's at rest. So let's do this to this equation. Let us pull it down to the number 4. So let's go down 4 inches and let it go, and let's see what that spring's going to look like. The spring's going to go up and down, up and down, up and down. So notice what I did here. So this equation is modeling that I pulled it down 4 inches. That's our starting point here. So if I were to ask you, what is A? Remember, A is amplitude. Amplitude equals your maximum displacement from the equilibrium point. So let's think about what A is. If your equilibrium was here, and for A, I'm telling you that I pulled it down to 4 inches, what would be your A in this equation? Your A would be a -4 because you are pulling it down the 4 inches just to begin with. Now, a couple other things. When I'm looking at this graph, if I'm asking you to give me the equation that models this graph, let's think about my 2 options again. So my 2 options are amplitude cosine omega t or amplitude sine omega t. We can cross one of these off right away. Just by looking at this graph, you guys should be able to tell if it's a cosine or a sine function. So think for just a minute. One of these 2 always starts at 0, 0. The other one always either starts up or down a little bit. So this is a cosine function because our sine functions always go through 0, 0. So if I'm asking you guys to plug in your numbers here, we just said that it's going to follow this pattern, this function over here, and we just said that our A was -4. So the only thing I have left to find is omega. So let's do that on our next slide here. Given that one oscillation takes 3 seconds, now how did I know that, by the way? Well, if we look at our graph, to get from the starting point to a repeating pattern, to do one full cycle, as we call it, one full oscillation, that's at 3 seconds. So they're telling you it's 3, but they didn't even have to tell us that. We could see that from our own picture here. This means that the period of the function should be 3. What is omega equal to? So let's write out our formula that we talked about a couple slides ago for our period. So period equals 2 pi over omega. Our period is 3. 2 pi over omega. So now let's solve for omega. Multiply both sides by omega. So I get 3 omega equals 2 pi. So omega is going to be 2 pi over 3. So we just found that our omega is 2 pi over 3. So let me go back a slide and let's add that into our omega right here. Our omega is 2 pi over 3. So you guys were easily able to model the function that represents that graph. All you have to find is your A, which again is your maximum displacement, and your omega, which we used doing that formula that we just did. Now if I ask you what's frequency equal to, frequency is a slightly different equation. So frequency looks like this. Frequency equals 1 over your period, or you can also model it as omega over 2 pi. So we just found that our omega was 2 pi over 3. So we're going to divide that by 2 pi. You're going to do your omega, which is 2 pi over 3, divided by 2 pi. So remember when we're dividing fractions, we are going to change it to a multiply by the reciprocal. Okay, so I'm not quite sure where the recording lost us, but it kicked me out of the room. So just to quickly recap, frequency is 1 divided by period, which is omega divided by 2 pi. Here was our omega, here's our 2 pi. Instead of dividing for fractions, we're going to change it to multiply by the reciprocal. So 2 pi crosses with 2 pi, and I'm left with a frequency of 1/3. So if you have any questions about that, send me a email and let me know exactly which step you're stuck on, and I would be happy to help. So let me show you this example. My first question to you is it sinusoidal? So you should be able to look at a function and decide if it's sinusoidal. So yes, it's sinusoidal. How did I know? Because sine and cosine functions are considered sinusoidal. Next, can it be described as simple harmonic? Is it a simple harmonic motion, sinusoidal function? Wow, we have a lot of vocabulary words in there. So the question is does it follow the pattern? Is it written in this format? Oops, I guess I don't need a parenthesis there. Is it written as an amplitude out in front times sine times omega t? It sure is. So yes, it's simple harmonic because it follows the pattern of how we write the functions. Maximum displacement. Well, we learned earlier today that A equals the maximum displacement. So if I'm looking at my equation, where's A? A is the number in front of sine, so what number is in front of sine? 6. So your maximum displacement is 6. That means it's going to go up 6, it starts up 6, and then it's going to go down 6. And then lastly, knowing our vocabulary, displacement is also called amplitude. That just might show up on the test. So know those vocabulary words. Amplitude. So our second kind of motion that we're going to deal with, we just did some spring problems, are pendulum problems. Now pendulums are a little bit different than springs because springs go up and down. Well, pendulums go side to side. If you've ever played the piano and you have one of those pendulums that sort of clicks to keep time to the music, that's considered a pendulum. It's like a clicking pendulum. So our motion of our pendulum, here's the difference. Our actual displacement, remember before we were talking displacement is how much up or down it is from equilibrium? Well, here it's sort of the same thing, but think about this. If your pendulum starts here at my bottom blue dot and it swings out to this blue dot, your actual displacement is an arc. That's interesting. Your actual displacement is this arc right here. But what we're going to learn is that when this angle is really small, we can just use this length. This length is going to be so close to the curved arc length because our angle is so small. So that's what this unit is telling us to do. Later on we'll talk about arc length, but for now I want you to understand the actual displacement really is this curved arc because that's where the pendulum's going. It's starting down here at the bottom and it's ending up over here. But the way that they're going to show us to do it in Pre-Calc is they're saying when this angle is super small, this straight line is very, very close to this curved line. So let's try some. Here are your formulas, and again, these are just so that you have them in your notes. I will also share this PowerPoint with you guys, that way you'll have a copy of it. So let me do that right now while you're taking some notes if you would like to. It's just the period and the frequency for pendulums. Okay, so the PowerPoint is coming your way. When you get it, you can save it, you can print it, do what you would like to do with it. So the capital L is going to stand for the length of our pendulum. That's going to come in very handy to us. So when I'm looking at this picture, this is your capital L. This is the length of the pendulum. So from where it starts to that ball that hangs at the end, that's the length of the pendulum. And then with pendulums, we also have to include the gravitational pull, because when something's swinging side to side, gravity is help pulling it down. This will come into play with physics too if you guys are also enrolled in physics class. So we're going to try one together. Here we go. If I could spell right. A pendulum. Very nice, Mrs. G. Okay, a pendulum. A 30 centimeter pendulum swings from 34 centimeters to 16 centimeters. Let's mark those spots on my graph. 34 centimeters. Sorry about that, got kicked out again. Gotta love Illuminate this morning. So this pendulum is going to go from 34 inches, let's make a little mark on our graph, to 16 inches, making another mark on our graph. And it's telling me that the pendulum itself is 30 centimeters. So let's mark that on my picture. Let's make the pendulum 30 centimeters. What is the equilibrium? So remember, the equilibrium is going to be the place where it is at rest, where it's sitting at rest, where it's not moving. So let's try. How we're going to find the exact middle is we're going to take our two numbers and subtract them. So 18 is my displacement. Displacement, there we go. That is how much is in between those two numbers. There are 18 inches between our two numbers. 18 is my displacement. But how am I going to find the place where it rests exactly? Well, the place where it rests exactly is going to be halfway in between these two. So you could add them together and divide by 2, or we can just say if my displacement is 18, half of 18 would be 9. So if I start at 16 and I go in 9, think about where you would be. We'd be at 25. So 25 is my exact middle. That is going to be my place of equilibrium. So it's in between our two extremes of where the pendulum swings. It's the exact middle of those spots. So that's our equilibrium. Now let's try this one. How can we use horizontal displacement to find angular displacement? So remember before I was telling you that when the angle is super small, we are able to use the horizontal displacement. So let me show you real fast again. Come back here. So when our angle is super small, we are able to use the horizontal displacement to help us figure out the actual displacement. So here we go. Let's try it. Basically what we're going to do is we're going to draw an inner triangle that goes straight through our equilibrium. Here's my triangle. So I'm going to redraw my triangle down here at the bottom. So that way I have a little more space. So let's think about what I know here. I know that my pendulum is 30 centimeters. So that means this is 30 centimeters. So let's label it. I know that from my middle, my equilibrium point to the end of the pendulum, how many inches did we say that was? We said the whole displacement was 18, which means from my equilibrium point to just my edge, my absolute extreme would be 9. Okay, think about if that makes sense for a minute. We learned that my whole displacement from 16 to 34 was 18. So that means at its maximum point, it's going to be 9, distance of 9. From here, it's just a simple sine equation. So we're going to say sine theta equals opposite over hypotenuse. If we were to actually work this out, in order to solve this function, remember you would have to go second sine. You have to do the inverse of sine on your calculator. So you go second sine so that it looks like this. Sine's the -1. And then we type in 9 divided by 30. And when we do that, we get 0.3046. But what that little formula was telling us before is that when theta is super small, sine theta is going to be the exact same as just theta. Meaning, if I don't even include the sign, if we just do 9 over 30, watch what I'm going to get. I get 0.3. Aren't these answers super close? So whether I'm calculating the exact distance or the approximate distance, they're going to be the same. So they're just giving you a rule to use. They're just saying you can do sine theta, or you can just do theta, which is the fraction opposite over hypotenuse, and you are going to get really, really close to the exact same answer. So they're giving you a way to do it without using your trig functions. That's part. So that's just part of what they were teaching you, is either that you guys could use your trig functions to solve, or you have a way to solve it without trig functions, and they are super close to the same answer. Okay, lastly for today, this is called Hooke's Law. Hooke's Law are springs that are horizontal, and it's when a force is being applied against a spring, for instance, in a car engine. Forces are being applied against springs for your piston pins to work and all that stuff. So these can be pushed or pulled. So just like when we were talking about the spring that's hanging here, we can pull it down or we can push it up. Horizontal springs are going to work the same way. You can add force going to the right, pushing it, or you could pull back on it. Here's the equation for Hooke's Law. We really don't use it very much in pre-calculus. I just wanted to show you that it is connected to physics. So here's some test tips. Keep your unit circle handy. Remember, it's your best friend. Have it totally labeled, because that's what the first few sections were in Unit 3, was using it to find, tangent to the -1 of root 2 over 2. So keep your unit circle handy. When you use the unit circle and find the values of your trig functions, it's really not much different than solving a regular equation. We found that to be true last week. And then lastly, simple harmonic motion equations are the same as functions in Unit 2. We just have different symbols. So don't let our new symbols scare us. We have our amplitude, we have our omega, and our time. So just use your formulas for solving for omega. Your amplitude, you can tell what it is just by looking at the graph and how much it has been displaced. So I feel like you guys are ready to go. You're going to rock this test. Remember to do the 3.5 practice, or 3.4 practice, I believe it is. Turn it into the Dropbox, and once you turn it in, send me a K-mail so that I will give you the answer key. So I hope that you have a great week. Finish up Unit 3 before spring break next week, and then you can come back and we'll start with Unit 4, clean, fresh slate. All right, thanks guys. Have a great day. Here's just a reminder of your essential question. It's what is the difference between frequency and period of a sinusoidal function?